Hello, and welcome to this video presentation. Most of you will have heard about vector computers in the past. Maybe some of you have even worked with a vector supercomputer at university or at a research institution. From the mid-1990s, the vector architecture played an important role in supercomputing, and vector computers were leading the top 500 for a substantial time. NEC is still developing vector processors to this day and will continue to do so for the foreseeable future. This presentation gives you an overview of the modern-day vector architecture with the goal of maximum sustained application performance. History shows that NEC has developed vector supercomputers for 35 years. One important highlight, the Earth simulator, which you all probably have heard of, was number one in the top 500 from June 2002 to 2004. It was based on an SX6. Development continued throughout the years until the last of the big iron vector supercomputers, the SX-Ace, was introduced in 2011. Nowadays, NEC offers a complete range of HPC solutions, including hybrid solutions and vector solutions. Of course, we also develop scalar systems, Linux clusters, and scalable appliances for high-performance storage. NEC offers the complete range of services alongside the hardware: system integration, software development, complete service and support. But we also have benchmarkers and an R&D department, and we can help you with application tuning, especially for the vector architecture. This NEC expertise leads to the ultimate goal of maximum sustained application performance. Now let's talk about the new architecture, the SX-Aurora TSUBASA. TSUBASA means wing, by the way, in Japanese. It has been shown that the big iron is very expensive to develop and produce. So nowadays, what we do is develop a vector processor as a vector engine in the form factor of a PCIe card. This PCIe card is simply plugged into a standard x86 Linux server, much like a GPU, but works a lot differently. This enables you to enjoy really high performance with easy programming. NEC provides the whole software environment, including, of course, Linux, the NEC vectorization compiler for your standard programming languages, Fortran, C, C++, without any need for special programming, such as CUDA, is all not necessary. The standard x86 server takes care of all the I/O and enables an interconnect with InfiniBand and even direct communication between the vector engines. The product overview gives you an impression about what can be done. The simplest instance is a workstation with one vector engine. Can be used as a desk-side workstation for development, in laboratories, for testing, for software development, and so on. Rack mount servers are available with 2 or 4 cards or 8 cards. And of course, the supercomputer, the A500 or today's A511, comes as a whole rack. We also offer all sorts of cooling. DLC cooling is available at the supercomputer. Water cooling doors may be used in rack mount systems or for rack mount systems. And the workstation is of course air cooled. The product line shows 2 tower models, with each with one vector engine, or 1 card. Type B is supported and Type CE is supported as well. There are rack mount systems with 2 or 4 cards, with 6 or 8 cards, and a supercomputer with up to 64 vector engines and vector engine type 10AE. If you have a vector supercomputer, one rack will provide more than 150 teraflops. There are also even denser solutions that we can provide upon request. Most systems are air-cooled or indirectly water-cooled, for example, with side coolers or cooling backdoor. And direct liquid cooling is available for the supercomputer, the A511. All of these systems are currently available. The vector engines themselves today come in 4 types. The largest one is type 10AE, featuring 8 vector cores, and I mean vector cores with real vector registers and real vector pipelines at a frequency of 1.584 gigahertz. And a single core provides more than 300 gigaflops of peak performance. That is much, much more than a scalar processor can achieve nowadays. You compare it, a high-level scalar processor with AVX512 enabled, provides up to about 80 gigaflops, whereas this vector core, a single core, gives you more than 300 gigaflops of peak performance. It has 48 gigabytes of HBM2 memory, very, very fast memory, with a memory bandwidth of 1.35 terabyte per second, which is huge, and gives you a very, very good byte per flop ratio. Type B is clocked at 1.4 gigahertz, almost as type 10BE, which is a successor to that, clocked at 1.408 gigahertz. And the memory bandwidth of the E types is 1.35 terabytes per second, whereas the 10B is 1.22 terabytes per second, is available in the workstation tower. Memory capacity for B and BE is also 48 gigabytes. And I always recommend the 10BE as the SKU with the best price performance ratio, really, because it has the full number of cores and the full memory bandwidth, the full memory capacity, just a little bit, a slightly lower processor clock frequency. Type 10CE can be used for applications that don't need a lot of memory, but are vectorizable as well. It only has half the memory capacity and the memory bandwidth of exactly 1 terabyte per second, which may be enough for many applications nowadays. All of these vector processors come as a PCIe 3.0 card, as you can see here. It can be directly liquid cooled or passively air cooled or actively air cooled with a fan in the tower workstation. Now, here's a workstation, and you can see the inner workings. Is a Xeon processor based on Cascade Lake, gold 6200 or silver 4200, depending on your application, whether you need scalar performance or not. And a direct connection to the vector engine. The rack mount system, A311, features up to 4 vector engines. There's 1, 2, 3, and there's a 4th one here. And 2 InfiniBand cards. So they are already prepared for clustering. They have 2 Xeon processors of this Cascade Lake type and up to 4 vector engines. A311-8 can be equipped with 6 or 8 vector engines and 2 InfiniBand cards. They have 2 Xeon processors. And the alternative is to use, if you need a lot of communication and a lot of bandwidth in the fabric, you can equip them with 6 vector engines and up to 4 InfiniBand cards. Now I hear you ask, are there any installations? What are the references? But there is a very large installation at DWD, the German Meteorological Service. They have acquired 2 large systems last year, and is currently in phase 1. Phase 0 has been concluded. Currently, phase 1 features 224 vector hosts with 8 vector engines each. You can see it's A312 here is a bit of a special SKU that has a lot more density in a rack. With altogether 1,792 vector engines of type 10B and a peak performance of roughly 4.36 petaflops. The second system currently has 292 vector hosts with 2,336 vector engines and 5.6 or 5.68 petaflops peak performance. After the final phase, starting next year, the systems will have 8.25 petaflops and 10.82 petaflops peak performance respectively. And you can see a picture of the current installation at DWD here below. So there are systems and they are working well. They are currently doing the weather forecast for Germany and part of Western Europe. The specification for the processor with an example of vector engine 10AE is as follows. Each core supports a vector length of 256 words of 64-bit each. That's 16 kilobits or 2 kilobytes vector length. 8 cores at a frequency of 1.584 gigahertz provide a double precision floating point peak performance of 304 gigaflops, or single precision, double that value, 608 gigaflops. The whole CPU with 8 cores therefore has a double precision peak performance of 2.4 teraflops and single precision of 4.8. There is a software controllable cache of 16 megabytes that's shared among the cores, and a memory bandwidth from that cache to the HBM2 memory, which is stacked sixfold, of 1.35 terabytes per second. Memory capacity in the case of Vector Engine 10AE is 48 gigabytes. The implementation of the CPU is as follows. HBM2 memory tiles are connected to the HBM2 interface on a silicon interposer with a last level cache of 2 times 8 megabytes and a 2D mesh on which the cores sit. So each core is connected to the neighbors and the last level cache. The bandwidth per core is about 400 gigabytes per second. So 4 cores will be able to saturate the memory bandwidth at full speed. Now, what is the difference between GPU PCI cards and the Vector Engine PCI cards in terms of programming and application performance? GPUs typically use an acceleration model. So it's an offloading model. Application typically offloads functions to the GPU. Therefore, you have frequent transactions over the PCIe bus, which unfortunately makes the process slower, the application slower. With the SX-Aurora TSUBASA vector engine, the whole application is loaded into the vector engine and executed there. So there is hardly any transfer over the PCIe bus except for some system calls for I/O. Of course, it is possible to use it as an accelerator with offload models. But if you have an application that is well vectorizable, it should be possible to upload the whole application into the vector engine and execute it there. Offload models, as I said, are available as well. So you should run the application the right way. An OS offload is what I just described. There's also an offload from the x86 system to the vector engine, which is called VEO. So you can run your application on an x86 server and then offload the vector engine parts, the vectorizable parts, to the vector engine. The opposite is also possible, to execute the application on the vector engine and offload scalar parts, where the scalar processor is much better than the vector engine, to the x86 system. So it's a very flexible model and a very flexible solution. The programming environment, software development, is comprised of mainly standards compliant compilers using MPI and highly optimized numeric libraries. There is a numeric library collection, the so-called NLC, NEC NLC, that you will see the features in the next slide. The compilers support automatic vectorization for Fortran C++, standard compliant automatic parallelization, and you can do your programming just with common knowledge, but of course keeping in the back of your head vectors. So you think vector, you don't think scalar when you start developing such an application. The numeric library collection contains a lot of functions that are optimized for the architecture, which includes dense matrix with basic operations, simultaneous equations, and so on, sparse matrix, transform operations, and statistics. And you can see there are some functions, some routines in the NLC that you can find nowhere else, not in the MKL from Intel, not in CUDA libraries. And NEC also plans and is actively working on different AI functions for this vector engine. So how can we contribute to your research and development efforts? There are a number of reasons why you want to use SX-Aurora TSUBASA, vector processor, vector architecture. It is a proven product. The architecture itself has been in the market for 35 years. It's vector. And vector technology is fast if you vectorize correctly. You can reuse old vector codes. Why not try them? And you should use your time for research and development and not for programming in strange languages like CUDA. Typically, there is a lot of machine time and no queues, especially if you have a desk-side workstation. You can use it for AI, machine learning, and of course for HPC. If you want to do research on hybrid architectures, that is a very, very good research subject. It is affordable for personal using, especially the desktop workstation. And above all, if you remember the olden times at university, vector computers are fun. So, thank you very much, and I'll be happy to take your questions.